We are now in a position to prove the structure theorem for finitely generated modules over a principal ideal domain. So let R be a principal ideal domain, and suppose N is a finitely generated R module. So we can assume that M is generated by some finite set of elements, say generated by x1, x2, xm for some positive integer m. Then using these generators, we can construct an R module homomorphism P from R to the power n to n by P takes the ith coordinate vector here, which we are calling Ei to xn. And the fact that M is generated by x1, x2, xn implies that this P is projected. And therefore, M is isomorphic to Rm mod kernel. Now, kernel C is a submodule of M, and since R is a principal ideal domain, it's also a Noetherian ring, and therefore kernel C being a submodule of a finitely generated R module is again finitely generated. So let's say kernel C is generated by vectors, let's call them v1, v2, v. So these are vectors in R to the m. I'm going to think of them as columns. So then you form the matrix whose columns are these vectors v1, v2, vn. And so this matrix has m rows and n columns. And what we're saying is that kernel C is the column space. Okay. So what we have is M is isomorphic to Rm mod the kernel space of not the kernel, okay, the column space. Okay, so we have expressed our module, finitely generated R module, in terms of a finite set of generators and a finite set of relations, which we have represented by this M by N matrix. Now we know that Rm mod column space of A is isomorphic to Rm mod column space of B if and only if A is similar to B. So let's use that. So we also know that A is similar to a matrix in Smith normal form. So suppose A is Smith normal form. Let's call it B, and that's B1, B2, BR, and then zeros everywhere. This is in this as well. Then what we have is that M is isomorphic to Rm mod column space of A, but A is equivalent to B, so M is isomorphic to Rm mod column space of B. But Rm mod column space of B, well, what we are saying here, this the column space of B means this is the submodule generated by D1 times E1 the submodule generated by D1 E1, D2 E2, dr dr. So these vectors get killed in Rm to give you something isomorphic to M. So this is just the same as R mod d1 direct sum R mod d2 direct sum R mod dr, and beyond that it's R mod 0. So it's direct sum R to the power of so the number of columns here is n minus 5. Now it's possible, quite possible, that some of these we have also this condition that d1, the ideal generated by d1, is larger than or equal to the ideal generated by d2. It's larger than or equal to the ideal generated by d1. Now it's quite possible that some of these d1, d2 and so on are units, but if in that case R mod di is going to be trivial. So disregarding those, what we get is, therefore M is isomorphic to an R module of the form R mod. So now I might renumber these as in throw out the first few di's which are units, but and renumbering things and so on, maybe changing R if necessary. But what we get is R mod dr direct sum R mod f for some. So this, now none of these are units. I have just disregarded the di's that are units, and so we have that this is a proper ideal. d1 contains d2 contains, and sum f greater than or equal. What we see is that every finitely generated R module is a direct sum of what are called cyclic R modules. R modules are the form R mod di for some element di of R, and moreover these elements d1, d2, dr can be chosen in such a way that the ideal generated by d1 contains the ideal generated by d2, in turn contains the ideal generated by d3, and so on. And then there's again a free part, this R mod f. So every finitely generated R module is a direct sum of a finite number of cyclic modules. Moreover, we can assume that the generators of the kernel have this containment. So this note is equivalent to d1 divide d2 divide di. We have seen that every finitely generated R module is a sum of R mod d1 plus dot 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 R mod dr plus some copies of R. Now the question is this decomposition unique? So now suppose we have that M is isomorphic to let's say Rm mod column space of d1, d2, dr, and at the same time it is also isomorphic to R of some other k mod column space of e1, e2, es. Right? Even the number of generators, we may have taken a lot of generators, a lot more than we needed, and so it's not even clear that M should be equal to k a priori. So let's assume that k is less than M, just without loss of generality. So then what we can do is we can always change this a little bit and make k equal to M. So what we can do is we can make this Rm mod column space of, and then I'll put a bunch of ones here. How many ones? I'll put M minus k ones. So these will contribute R mod 1 m minus k copies of R mod 1, which is just 0, so it will not change the isomorphism class. And then I'll put E1, E2, Es 0, 0. So what we have is now that M is isomorphic to Rm mod the column space of this matrix or Rm mod the column space of this matrix. But we've already shown that Rm mod column space of A is isomorphic to Rm mod column space of B if and only if A is equivalent to B. That would mean that this matrix d1, d2, dr is equivalent to this matrix with a bunch of 1s and then E1, E2, Es. But by the uniqueness of Smith canonical form, this means that these two matrices are actually equal. And since we've assumed that R is that D1 is a proper ideal of R, it's not, D1 is not a unit. This implies that M minus K is 0. So implies that M minus K is 0, i.e. M is equal to K. And moreover, by the uniqueness of Smith canonical form, it follows that R equals S and Di equals Ei for all I. So we have just proved the structure theorem for finitely generated R modules. Let me write down the statement clearly. Every finitely generated R module M is isomorphic to R mod D1 plus R mod dr plus R to the power F for some D1 contained D2 containing dr, and in fact we assume that D1 is not equal to R and some non-negative integer f. So moreover, R, F and the ideals D1, D2, dr are uniquely determined by M. That's the structure theorem for finitely generated modules over a principal ideal domain. So here I should say let R be PID. We use that, of course, right? That's the theorem.